Tonight, we're going to talk about how we measure the universe. When you look up at the night sky, every star you see is separated from us by distances that are almost impossible to comprehend. Trillions upon trillions of miles. And astronomers have a special unit they use to measure these cosmic distances, the parsec. You've probably heard this word before, but almost nobody stops to ask the obvious question. What actually is a parsec, and why does it exist? Here's what's going to surprise you. The parsec isn't based on anything natural about the universe. It's not tied to the speed of light, not connected to any fundamental constant, not marking any cosmic boundary. It's a measurement that makes absolutely no sense, built on ancient angle systems that have nothing to do with the cosmos. And by the end of tonight, you're going to discover why this bizarre unit dominates professional astronomy and why the cost of changing it is so high that we're stuck with it forever. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. To understand why the parsec exists, we need to go back to a fundamental problem that plagued humanity for thousands of years. How far away are the stars? Look up at the night sky on a clear evening. You see thousands of stars scattered across the darkness. Some appear bright, some dim. Some are clustered together in patterns we call constellations. But how far away are they? For most of human history, we had absolutely no idea. The ancient Greeks made educated guesses. Some thought the stars might be attached to a crystalline sphere just beyond Saturn. Others thought they might be much farther, but had no way to measure. Ptolemy in the 2nd century placed the sphere of stars just beyond the planets. This seemed reasonable at the time because stars showed no apparent motion relative to Earth. If they were close and Earth moved, you'd expect to see them shift position throughout the year, just like nearby trees appear to shift against distant mountains when you walk past them. Since no shift was observed, either the stars were incredibly far away or Earth didn't move. Most ancient and medieval astronomers concluded Earth didn't move. This fit with the geocentric model, the idea that Earth sat stationary at the center of the universe while everything else rotated around it. The stars were fixed on their sphere, perhaps only a few million miles beyond Saturn, close enough that their lack of observed motion made sense. This view persisted for well over 1,000 years. In 1543, Nicolaus Copernicus published his revolutionary work proposing that Earth orbited the Sun, not the other way around. This heliocentric model solved many problems with predicting planetary motions, but it created one glaring issue. If Earth moves around the Sun, completing a full orbit every year, then nearby stars should appear to shift position against more distant background stars. This effect is called parallax, and it's something you experience constantly in everyday life. Hold your thumb up at arm's length. Close your left eye and note where your thumb appears against the background. Now close your right eye and open your left. Your thumb appears to jump to a different position. This happens because your two eyes view your thumb from slightly different angles. Your eyes are separated by about 6 centimeters, so they see slightly different perspectives. The closer an object is to you, the larger the shift. Try the thumb experiment again, but this time hold your thumb closer to your face. The shift is much larger. Now look at something across the room. The shift is much smaller. Something a mile away shows essentially no shift at all, because the 6 centimeter separation between your eyes is insignificant compared to a mile. The same principle applies to stars. If Earth orbits the Sun, we're viewing the stars from different positions throughout the year. In January, Earth is on one side of its orbit. 6 months later, in July, Earth is on the opposite side. The distance between these two positions is enormous, 186 million miles. This is called Earth's orbital diameter, twice the distance from Earth to the Sun. Viewing the stars from positions separated by this vast distance should cause nearby stars to shift against the more distant stellar background. This stellar parallax should be measurable if stars aren't infinitely far away. Copernicus knew this. He knew his heliocentric model predicted stellar parallax. When critics pointed out that no parallax had been observed, Copernicus had only one answer: the stars must be incredibly far away, so far that even Earth's enormous orbital motion produces a shift too small to measure with the naked eye or the crude instruments of his time. This was actually the correct answer, but it was also somewhat unsatisfying. Copernicus was essentially saying, "My theory predicts an effect. You can't see that effect. Therefore, the effect must be too small to see." It's logically consistent, but not very convincing to skeptics. For the heliocentric model to be truly accepted, someone needed to actually measure stellar parallax. This became one of astronomy's great challenges. Find the parallax, prove Earth moves, and simultaneously measure the distance to the stars. Johannes Kepler had established that Earth orbits the Sun in a roughly circular path. By the mid-1600s, astronomers had measured Earth's orbital size fairly accurately by observing transits of Venus across the Sun's face. They knew Earth orbits in a path about 300 million miles in diameter. That's 186 million miles. This means that in January, Earth is on one side of the Sun, and 6 months later in July, Earth is on the complete opposite side. Observe a star in January. Note its exact position against the background of more distant stars. Then observe the same star in July from the opposite side of the orbit. You're viewing from two positions separated by that full diameter. It's like having eyes separated by 300 million miles instead of 6 centimeters. Even the nearest stars should show a tiny shift against the more distant background stars. This shift is called stellar parallax. Measure this shift, use basic trigonometry, and you can calculate the distance. The concept is beautifully simple. Draw a triangle. The base is Earth's orbit diameter. The vertex is the star. Measure the angle at the star, and you can calculate how far away it is. Simple geometry that any student learns in school. The execution, however, proved nearly impossible. The problem was that the shift is incredibly tiny. We're talking about angles smaller than 1 arcsecond. To understand how small 1 arcsecond is, imagine dividing a degree into 60 parts. Each part is 1 arc minute. Now divide each arc minute into 60 more parts. Each of those is 1 arcsecond. So 1 arcsecond is 1/3600th of a degree. To give you a physical sense of this, if you hold a tennis ball at the distance of 1 mile, the ball appears about 1 arcsecond wide. If you're standing on a beach and you see a ship on the horizon 10 miles away, a person standing on that ship's deck appears about 1 arcsecond tall. That's the kind of precision 17th century telescopes would need to detect stellar parallax. They couldn't do it. The best telescopes of the time had mechanical wobbles larger than the signal astronomers were trying to detect. Atmospheric turbulence blurred images by several arcseconds. Temperature changes made telescope parts expand and contract by amounts that threw off alignment. Even the astronomer's own heartbeat could introduce vibrations large enough to ruin measurements. The foundations of observatory buildings settled and shifted with temperature. Wind pushed on telescope tubes. Robert Hooke tried in 1669. He was a brilliant scientist, one of England's leading experimentalists. Hooke had contributed to optics, mechanics, astronomy, and biology. He coined the word cell after seeing the structure of cork under a microscope. He formulated Hooke's law of elasticity. He was a serious scientist tackling a serious problem. Hooke built a special telescope mounted in a tall building to minimize atmospheric distortion. The idea was that mounting the telescope high up would put it above some of the turbulent air near the ground. He observed a bright star called Gamma Draconis for months, took careful measurements, detected what he thought was a shift in position. He published his findings, claiming to have measured stellar parallax at last. He was wrong. What he had actually detected was something called stellar aberration, a different effect entirely that comes from the combination of light's finite speed and Earth's motion through space. Here's how aberration works. Light travels at finite speed, about 186,000 miles per second. Earth is moving around the Sun at about 19 miles per second. When you point a telescope at a star, you have to tilt it slightly in the direction of Earth's motion to compensate for the fact that light is traveling down the tube while Earth is moving sideways. It's like running through rain. Even if the rain is falling straight down, you have to tilt your umbrella forward because you're moving horizontally. This aberration effect is real and measurable. But it's not parallax. Parallax makes nearby stars shift against distant background stars. Aberration makes all stars shift in the same direction by the same amount. Hooke had discovered something real and interesting, just not what he thought he'd discovered. The actual discovery of aberration is credited to James Bradley in 1728, who figured out what was really happening. William Herschel tried a different approach. Herschel was the astronomer who discovered Uranus in 1781. The first planet discovered in recorded history. Before Uranus, humanity knew 5 planets, Mercury through Saturn, all visible to the naked eye and known since ancient times. Herschel's discovery of a 6th planet made him instantly famous. He reasoned that if you observe double stars, pairs of stars that appear close together in the sky, one star in the pair might be much nearer to Earth than its companion. If so, the near star should show parallax, while the distant one doesn't. Over many years, he made thousands of painstaking measurements of double star systems, carefully tracking the angular separation between the components of each pair. He never found parallax. But his work wasn't wasted. He discovered that many double stars aren't just chance alignments, 2 unrelated stars that happen to lie along the same line of sight from Earth. They actually orbit each other gravitationally. He had discovered binary star systems, pairs of stars bound together by gravity, orbiting their common center of mass. This turned out to be one of astronomy's most important discoveries. Binary stars became crucial tools for measuring stellar masses. By watching how fast 2 stars orbit each other and measuring their separation, you can calculate their masses using Newton's laws. This is still how we measure most stellar masses today. Herschel's failed attempt to find parallax led to a discovery that transformed stellar astronomy. By the early 1800s, measuring stellar parallax had become astronomy's great challenge. It was the Holy Grail. Everyone knew it should be possible in principle, but nobody could actually do it. The failure wasn't from lack of trying. Dozens of skilled astronomers across Europe spent years on the problem. Some claimed success, publishing measurements that other astronomers couldn't replicate. The claimed distances varied wildly, suggesting the measurements weren't reliable. The distances were too great, and the measurement too difficult for the instruments of the time. Friedrich Wilhelm Bessel was different from his predecessors. He was German, born in 1784 in the town of Minden in Westphalia. Interestingly, Bessel didn't start out as an astronomer. He began his career as an accountant for a trading company, but he taught himself mathematics and astronomy in his spare time. He was particularly interested in navigation and studied how to calculate positions using astronomical observations. At age 20, Bessel calculated the orbit of Halley's Comet using old observations. He did this purely as a hobby, but his work was so good that a professional astronomer, Heinrich Wilhelm Olbers, noticed it and helped Bessel get a position as an assistant at a small observatory. By age 26, Bessel was appointed director of a new observatory being built in Königsberg. He would spend the rest of his career there, making it one of Europe's leading observatories through the quality of his work. Bessel became one of the most meticulous scientists of his generation. He was obsessed with precision and error analysis. This was still a time when many scientists took measurements somewhat casually, writing down whatever their instruments showed without carefully considering all the sources of error. Bessel was different. He didn't just take measurements. He analyzed his instruments in exhaustive detail to understand their limitations. He calibrated everything repeatedly. He developed mathematical techniques to account for known error sources. He invented what we now call Bessel functions, a class of mathematical functions used to solve certain types of differential equations that arise in physics and engineering. These functions are still used today in everything from antenna design to quantum mechanics. That's the level of mathematical sophistication Bessel brought to observational astronomy. In the 1820s and early 1830s, Bessel set his sights on stellar parallax. He knew the challenge required exceptional precision, better instruments than anyone had used before, and rigorous error analysis. First, he needed the best telescope available. Bessel commissioned Joseph von Fraunhofer, Germany's premier telescope maker, to build a custom heliometer. A heliometer is a special type of telescope designed for making precise angular measurements. It has a split objective lens that can be adjusted to measure small angles very accurately. Fraunhofer delivered an exceptional instrument, representing the cutting edge of 1830s technology. Second, Bessel needed to choose the right target star. He didn't pick just any bright star. He looked for a star with certain characteristics that would make parallax easier to detect. The ideal target would be relatively nearby, which typically means it should show large proper motion. Proper motion is a star's movement across the sky over years due to its actual motion through space relative to the sun. Stars aren't fixed in absolute space. They're all moving, orbiting the galactic center, moving relative to each other. A nearby star moving through space will appear to change position against more distant stars over time, completely separate from parallax. But the fact that a star shows large proper motion suggests it's relatively close. Distant stars show little proper motion because their vast distance makes any transverse motion appear tiny. Bessel chose a star called 61 Cygni. This star, in the constellation Cygnus, had the largest known proper motion of any star at the time, discovered by Giuseppe Piazzi in 1804. It moves about 5 arcseconds per year across the sky, which is enormous by stellar standards. This large proper motion strongly suggested 61. Cygni was relatively nearby, making it a good parallax candidate. The star is also moderately bright, which helps with precise position measurements, and it has several dimmer stars nearby that could serve as reference points for measuring parallax shifts. Perfect. Third, Bessel needed a rigorous observational plan. He would observe 61 Cygni throughout an entire year, taking measurements as frequently as weather permitted. He would measure the star's position relative to several nearby reference stars, carefully tracking how the angular separations changed over time. He would observe from the same location using the same instrument to eliminate variations from changing equipment. And critically, he would account for every possible source of error: temperature effects on the telescope, atmospheric refraction, bending starlight as it passes through Earth's atmosphere, the aberration effect that had fooled Hooke, precession of Earth's axis, proper motion of the target star. Every known effect would get its own mathematical correction. Bessel began his observations in August 1837. He observed almost every clear night for 13 months. Each observation involved multiple careful measurements of 61 Cygni's position relative to surrounding reference stars. Each measurement was recorded meticulously in his notebooks. After 13 months, Bessel had accumulated hundreds of position measurements spanning a complete orbit of Earth around the Sun. Now came the mathematical analysis. Remember, this is 1838. No computers, no calculators. Everything was done by hand, using logarithm tables. Bessel had to apply corrections for dozens of effects. He corrected for atmospheric refraction, which varies with altitude and temperature. He corrected for aberration, the effect that had confused Hooke. He corrected for precession, the slow wobble of Earth's axis that changes the coordinates of stars over time. He corrected for the proper motion of 61 Cygni, carefully separating its actual motion through space from the parallax effect he was trying to measure. He measured the expansion and contraction of his telescope with thermometers attached to the metal tube. He developed mathematical formulas relating temperature to telescope length. He built models of mechanical flexure. Every error source got its own mathematical treatment. Only after accounting for everything else, after months of painstaking analysis, could he isolate the tiny parallax signal buried in the noise. His result was 0.3136 arcseconds of parallax. To appreciate how small this is, imagine you're looking at a dime held at arm's length, about 60 centimeters away. The width of that dime, as seen from your eye, is an angle about 20,000 times larger than the parallax Bessel measured. He was measuring an angle approximately equal to the width of a human hair seen from 100 meters away, or the angle subtended by the period at the end of this sentence seen from across a football field. From this measurement, using basic trigonometry, Bessel calculated that 61 Cygni was about 10.3 light-years away. That's roughly 97 trillion miles. To put this in perspective, if you could somehow drive to 61 Cygni at highway speed, say 100 miles per hour, the trip would take about 110 million years. Modern measurements with better instruments give 11.4 light-years. So Bessel was remarkably close. His measurement was accurate to within about 10%. Extraordinary for 1838. This was extraordinary work. 13 months of nearly continuous observations, Bessel had to observe on every clear night, which in northern Germany means dealing with clouds, rain, and short winter days. He made hundreds of individual measurements. Then months of mathematical analysis, careful consideration of every possible error source, calculations done entirely by hand using logarithm tables because electronic calculators wouldn't exist for another century. It's precisely why nobody had succeeded before. The level of precision required was far beyond what seemed possible with 1838 technology. The measurement was at the very edge of what was physically achievable with the best instruments and techniques available. But Bessel managed it through pure, obsessive attention to detail, mathematical skill, and relentless patience. Within months of Bessel's announcement, in late 1838, the floodgates opened. Thomas Henderson, a Scottish astronomer working at the Royal Observatory in Cape Town, South Africa, published parallax measurements for Alpha Centauri. Interestingly, Henderson had actually made his observations before Bessel. Starting back in 1832, he had measured Alpha Centauri's position carefully over many months. But Henderson was cautious, perhaps too cautious. He saw a shift in position that looked like parallax, but he wasn't completely confident in his results. He worried about systematic errors. He questioned whether his instruments were accurate enough. So he sat on his data, continuing to analyze it, hesitating to publish. When Bessel's announcement came through in early 1839, Henderson realized his own measurements were valid and rushed to publish. His data was actually better than Bessel's in some ways because Alpha Centauri is brighter and closer, making the parallax larger and easier to measure. Alpha Centauri turned out to be even closer than 61 Cygni, at about 4.4 light-years. This is interesting from a history of science perspective. Henderson actually made the first stellar parallax measurements, but Bessel gets credit for the discovery because Bessel published first. This happens sometimes in science. The person who publishes first gets the credit, even if someone else did the work earlier. It's why scientists often rush to publish as soon as they have solid results. Friedrich Georg Wilhelm von Struve, working at the Dorpat Observatory in what's now Tartu, Estonia, measured Vega's parallax shortly after Bessel's and Henderson's announcements. Struve was another meticulous observer who had been working on the parallax problem for years. Vega is much farther than the other two stars, at about 25 light-years, making its parallax even tinier and harder to measure. Struve's measurement was less accurate than Bessel's or Henderson's, but it was still a genuine detection. Suddenly, after 2,000 years of complete mystery about stellar distances, we had distances to 3 stars, and more were coming. Astronomers worldwide began parallax programs. Within a few years, distances to dozens of stars had been measured. By the early 1900s, hundreds of stars had measured parallaxes. By the mid-20th century, thousands. Each measurement confirmed that stars were scattered at enormous distances, far beyond anything in the solar system. The nearest star, Alpha Centauri, was 40 trillion miles away. That's about 270,000 times farther than the Sun. Sirius, one of the brightest stars in our sky, and fairly close by stellar standards, was 81 trillion miles away. More distant stars were even farther. This discovery fundamentally changed humanity's understanding of the universe's scale. Before parallax measurements, some astronomers thought the Milky Way might be only a few thousand astronomical units across, perhaps 100 times the size of the solar system. After Bessel's work, it became clear the galaxy was millions of times larger. The Sun wasn't at the center of a small stellar system. It was one ordinary star among countless others scattered across distances so vast they were hard to comprehend. Our sense of cosmic scale expanded enormously. The universe went from being a solar system, plus a sphere of stars just beyond the planets, to being a vast space containing objects at distances requiring trillions of miles to describe. This was as revolutionary as Copernicus's discovery that Earth orbited the Sun, or Galileo's discovery that Jupiter had moons. But as these measurements accumulated, astronomers faced a practical problem. How do you communicate these enormous distances? Writing out 97 trillion miles gets tedious very quickly. Scientific papers were filled with huge numbers. Saying a star is at 657,000 astronomical units is awkward. Using multiples of the Sun's distance helped somewhat, but it still wasn't ideal. Someone, and history isn't entirely clear who first suggested it, proposed defining a new unit based directly on parallax geometry. The idea was beautifully simple and came naturally from the measurement technique itself. Take a right triangle. One side of the triangle, the base, is 1 astronomical unit, the distance from Earth to the Sun. The angle opposite that base, at the vertex where the star sits, is 1 arcsecond. Now solve for the length of the long side of the triangle, the hypotenuse, which is the distance to the star. Using basic trigonometry, specifically the tangent function, this distance works out to approximately 206,265 astronomical units. In more familiar terms, that's about 30.9 trillion miles, or about 19.2 trillion miles. They called this distance the Parsec, a contraction of parallax and arcsecond. The name itself tells you exactly how it's defined. Here's the crucial thing to understand. 1 arcsecond was chosen because it's a round number in the angular measurement system. humans invented thousands of years ago. The Babylonians around 2000 BCE developed a base 60 number system. They divided circles into 360 degrees because 360 has many factors. It's divisible by 2, 3, 4, 5, 6, 8, 9, 10, 12, and more. This makes it easy to divide circles into halves, thirds, quarters, and so on. They divided degrees into 60 arc minutes because 60 is also highly divisible, and they divided arc minutes into 60 arc seconds for the same reason. This sexagesimal system, based on the number 60, is why we still measure time in 60-second minutes and 60-minute hours. The Babylonians invented it, the Greeks adopted it, and it spread throughout the ancient world and persisted to today. But there's nothing physically special about this choice. It's pure mathematical convenience based on ancient numbering preferences. An alien civilization using a different angular system might divide circles into some other number of degrees and define their angular units differently. The parsec is a consequence of human choices about how to measure angles, not anything fundamental about the universe. And virtually no star sits exactly 1 parsec from Earth. Our nearest stellar neighbor, Proxima Centauri, is about 1.302 parsecs away, according to the latest Gaia satellite measurements. That's the most accurate distance we have, measured to 4 significant figures. The bright star Sirius, prominent in winter skies, is about 2.64 parsecs. Vega, one of the brightest stars in summer skies, is about 7.7 parsecs. Bessel's 61 Cygni is about 11.4 parsecs. The parsec doesn't mark any natural cosmic boundary. It's not the distance at which any particular physical process occurs. Stars don't start behaving differently at 1 parsec. There's no sphere of special significance at that distance. It's simply the distance that makes parallax arithmetic convenient, defined by an arbitrary angular choice, but that convenience turned out to be enormous for working astronomers. For astronomers doing parallax measurements every single day, the parsec had one massive advantage over any other distance unit. Measure a star's parallax in arcseconds, and its distance in parsecs is just 1 divided by that number. The relationship is direct and transparent. If a star shows a parallax of 0.5 arcseconds, it's 2 parsecs away. 0.2, 5 arcseconds, 4 parsecs. 0.1 arcseconds, 10 parsecs. 0.0, 5 arcseconds, 20 parsecs. Mental arithmetic, no calculator needed, no complex conversions, no looking up tables, just invert the parallax and you have the distance. When you're processing hundreds or thousands of measurements by hand, which is what astronomers did before computers, this directness is invaluable. Imagine you're working through a notebook full of parallax measurements. Star A, 0.15 arcseconds, that's 6.67 parsecs. Star B, 0.28 arcseconds, that's 3.57. Star C, 0.08 arcseconds, that's 12.5. You can do this math in your head while working through the observations. The relationship is transparent. If you measure a parallax of 0.05 arcseconds, you instantly know the distance is 20 parsecs. Compare this to using light years or miles. Converting parallax to light years requires knowing that 1 arcsecond of parallax corresponds to 3.26 light years, then doing division. Converting to miles requires knowing that 1 astronomical unit is 150 million miles, then using the tangent function, then multiplying by the appropriate conversion factors. It's doable, but it's extra steps, extra opportunities for arithmetic errors, extra time. The parsec eliminates all that. The measurement directly gives you the distance in the natural unit for the measurement. This mattered enormously in the pre-computer era. By the late 1800s, parallax measurements were becoming routine, and the parsec had become the standard unit in professional astronomy literature. Not because anyone mandated it, not because it was officially adopted by some governing body, but because astronomers found it useful and started using it. It spread through the field organically. Papers used parsecs. Textbooks taught parsecs. Students learned parsecs. Catalogues listed stellar distances in parsecs. The infrastructure of astronomy gradually came to assume parsecs as the distance unit. By the early 1900s, the parsec was completely entrenched. Now here's where things get interesting. The original reason for the parsec's existence, its usefulness for parallax work, has largely vanished. We don't measure stellar distances by parallax in quite the same way anymore. Modern parallax measurements are done by space telescopes like the Gaia mission, which launched in 2013 and has measured parallaxes for over 1 billion stars. Gaia's data processing is entirely automated. Computers handle all the calculations. No human astronomer is sitting there inverting parallax measurements by hand to get distances. The computer can convert to any unit instantaneously. Whether the output is parsecs, light years, miles, or units we invented yesterday, it makes no difference computationally. So why do we still use parsecs? The answer is institutional momentum and network effects. Changing units is easy in principle, but extraordinarily difficult in practice when an entire field has built infrastructure around a particular choice. Think about what would need to happen for astronomy to switch from parsecs to, say, light years. First, every existing catalogue of stellar positions and distances would need to be converted. We're talking about databases containing billions of measurements. Sure, computers can handle the conversion, but someone needs to write the software, test it, verify it's correct, and redeploy all the systems that use the old format. Second, every paper published over the past century reports distances in parsecs. If we switch units, either all that historical literature becomes harder to compare with new work, or someone needs to go through and convert historical measurements, which is massive work for marginal benefit. Third, every astronomer currently working has developed intuitions in parsecs. When you read that a star is 50 parsecs away, you have an instant sense of whether that's nearby or distant, whether you'd expect to resolve it with a certain telescope, what its apparent brightness should be given its luminosity. These intuitions took years to develop. They're based on experience with thousands of measurements. Switching units means retraining everyone's intuition. It means that when you read 10 light years, you need to mentally convert to 3 parsecs to use your existing understanding of cosmic scale. Fourth, all the software tools that astronomers use, from data reduction pipelines to analysis packages to plotting programs, assume parsec inputs. Some would need to be rewritten or updated. Others would need conversion factors built in. It's doable, but it's work. Work that takes time away from actual research. Fifth, and perhaps most importantly, there's no clear alternative that everyone agrees is better. Light years have the advantage of being more intuitive to the general public since they're defined by a fundamental constant, the speed of light, but they're actually less convenient for many astronomical calculations. Kilometers or miles are completely impractical because the numbers get too large. Astronomical units work for the solar system, but are too small for stellar distances. So if we abandon parsecs, what would we use? There's no obvious replacement that would make everyone's work easier. This is a common pattern in how standards emerge and persist. Once a standard becomes established, once infrastructure grows around it, once communities build their practices on top of it, changing requires coordinating across everyone simultaneously. The benefits of switching need to be enormous and clear to overcome the coordination costs and transition hassles. For the parsec, the benefits of switching are marginal at best. Sure, it's based on an arbitrary angular choice, but so what? It works. Astronomers understand it. The field functions well with it. The same thing happens in many domains. The QWERTY keyboard layout is famously inefficient, designed to slow down typists on mechanical typewriters to prevent key jams, but we still use it because switching would require everyone to relearn typing and would make existing keyboards obsolete. The width of railroad tracks in most countries is 4 feet 8.5 inches, because that's what George Stephenson chose for his early railways based on the width of horse-drawn coal wagons in English mines. It's completely arbitrary, but changing now would require replacing millions of miles of track and all existing rolling stock. The English measurement system of inches, feet, and miles is a bizarre collection of historical accidents. Yet, the United States still uses it because the switching costs are enormous. These arbitrary choices become locked in by network effects and infrastructure investment. The Parsec is astronomy's QWERTY keyboard. Now let me show you just how deeply parsecs are embedded in modern astronomy. The Gaia satellite I mentioned earlier is the most important astrometry mission ever flown. It's measuring the positions, distances, and motions of stars throughout the Milky Way with unprecedented precision. The mission is revolutionizing our understanding of galactic structure and stellar evolution. Gaia's main data products are massive catalogs listing properties of individual stars. The third data release in 2022 contained information on nearly 2 billion stars. For each star, the catalog lists coordinates, brightness, color, and crucially, parallax and distance. Every single distance in that catalog is reported in parsecs. Not light years, not miles, parsecs. This wasn't some arbitrary choice by the Gaia team. It was the only choice that made sense, given how astronomy works. The Gaia catalog is used by thousands of astronomers worldwide, studying everything from exoplanets to galactic dynamics to dark matter. All those astronomers expect distances in parsecs because that's what their analysis tools use, that's what their previous work used, that's what their intuitions are calibrated for. If Gaia reported distances in light years, every single user would need to convert to parsecs anyway for their work. So Gaia saves everyone that step by just reporting in parsecs from the start. This creates a feedback loop. Because Gaia uses parsecs, tools built to analyze Gaia data use parsecs. Because those tools use parsecs, new missions being planned use parsecs to maintain compatibility. Because new missions use parsecs, the next generation of astronomers learns parsecs, and so it continues, decade after decade. The parsec has become more than just a unit. It's become part of the conceptual framework of astronomy. When professional astronomers think about cosmic distances, they think in parsecs, not because parsecs are better in some absolute sense, but because that's the language their field speaks. And language, once established, is incredibly difficult to change. There's actually a beautiful parallel here to natural language. Languages are full of arbitrary features that make no logical sense. English has irregular verbs, silent letters, and bizarre spelling rules. Why is tough spelled with uff but pronounced like tough? Why is kernel pronounced kernel? These are historical accidents, remnants of how English evolved from various source languages. They make the language harder to learn and use, but we're stuck with them because coordinating a change across hundreds of millions of speakers is impossible. The parsec is astronomy's irregular verb. It's arbitrary, it makes the subject harder to learn, but it's too deeply embedded in practice to change. Let me give you a sense of just how arbitrary the parsec is by walking through its definition one more time. A parsec is the distance at which one astronomical unit subtends an angle of 1 arcsecond. The astronomical unit, Earth's average distance from the Sun, is itself somewhat arbitrary, but at least it's based on something physical in our solar system. But 1 arcsecond? That's 1/3600th of a degree. Why 360 degrees? Because the Babylonians liked 60 and chose 360 as a convenient number with many factors. Why did they like 60? Probably because you can count to 60 on your hands using your thumb to point at the 12 knuckles on your other 4 fingers, and using both hands, you can count 12 times 5, which equals 60. This is called the Babylonian finger counting system, and it's why we have 12 months, 12 hours on a clock face, and 60 seconds in a minute. But it's completely arbitrary. We could have divided circles into 400 degrees, or 1000 degrees, or anything else. Different cultures did use different systems. The ancient Chinese divided circles into 365¼ degrees to match the number of days in a year. Ancient India sometimes used 360 and sometimes 400. If astronomy had developed in a culture using a different angular system, the parsec would have a completely different value. Imagine an alternate history where the French revolutionary government's attempt to decimalize everything succeeded completely. In the 1790s, revolutionary France tried to reform measurements to be decimal-based. They succeeded with the metric system for length, mass, and volume. They also tried to decimalize time and angles. They proposed dividing the day into 10 hours, each hour into 100 minutes, each minute into 100 seconds. They proposed dividing the circle into 400 grads, each grad into 100 centesimal minutes, each minute into 100 centesimal seconds. Decimal time failed and was quickly abandoned, but decimal angles actually saw some use. Grads are still used in some surveying applications today. If decimal angles had become the global standard, if astronomers divided circles into 400 grads and measured parallax in centesimal units, the parsec would be defined completely differently. The math would work out differently, the numerical value would be different, and we'd have an entirely different unit, but it would serve the exact same purpose, converting parallax measurements to distances in a convenient way. This alternate parsec would be just as arbitrary, just as useful, and just as entrenched if history had gone differently. The parsec we actually use is a historical accident, a frozen consequence of choices made by ancient Mesopotamian mathematicians, who couldn't possibly have imagined their angular system would someday define the distance, scale of the cosmos. Here's another way to see the arbitrariness. The parsec only makes sense in the context of Earth's orbit around the Sun. If Earth orbited closer to the Sun or farther away, the astronomical unit would be different, and the parsec would be different. If we lived on a planet orbiting Alpha Centauri, which is a binary star system, we might define our baseline distance differently, and our version of the parsec would have a completely different value. If we were a spacefaring civilization that didn't orbit a star, maybe living in generation ships or on rogue planets drifting through interstellar space, we might not define a parsec at all. We might use some other distance unit based on different considerations. The parsec is Earth-centric, Sun-centric, and fundamentally parochial. It's useful for beings living in our particular solar system, using our particular angular conventions to measure distances to stars in our particular galaxy. But there's nothing universal about it. It's not a natural unit in the way that, say, the speed of light is natural. The speed of light is a fundamental constant of physics that any sufficiently advanced civilization anywhere in the universe would discover has the same value. 186,000 miles per second. It's a property of space-time itself, not a human convention. The parsec, by contrast, is entirely conventional. It's a unit we invented based on arbitrary choices about angle measurement and arbitrary facts about our planet's orbit. Another civilization might measure distances in completely different units based on their own conventions and circumstances. And yet, despite all this arbitrariness, despite the fact that the parsec is a historical accident frozen in institutional practice, it genuinely is useful for astronomers. That's the paradox. An arbitrary choice can still be a good choice if it serves its purpose well. The parsec serves its purpose. It provides a unit scaled appropriately for stellar distances, not too big, not too small. Nearby stars are a few parsecs away. Distant stars visible to the naked eye are hundreds of parsecs away. The galaxy is tens of thousands of parsecs across. Nearby galaxies are millions of parsecs away. The numbers come out reasonable at all scales, and for the original purpose, converting parallax measurements to distances, the parsec is genuinely elegant. It's built directly into the geometry of the measurement. You measure parallax, you have distance. No additional constants needed, no conversion factors, no looking up tables. For pre-computer era astronomy, this was a huge practical advantage. So while the parsec is undeniably arbitrary and often confusing to students and the public, it's not stupid. It's a reasonable choice that served its historical purpose well and continues to be good enough that switching has never seemed worth the trouble. This raises an interesting question about scientific practice and scientific units more generally. How many other units used in science are similarly arbitrary, frozen historical accidents that persist because changing is too difficult? Probably more than you'd think. Every scientific field has its own specialized units and conventions that developed for historical reasons and persist through institutional momentum. Chemistry uses moles, a unit based on the number of atoms in 12 grams of carbon-12. Why 12 grams? Why carbon-12? Historical accidents related to how atomic weights were originally measured and standardized. We could define the mole differently, but changing would require rewriting every chemistry textbook and adjusting every chemical equation. Particle physics uses electron volts for energy, where 1 electron volt is the energy gained by an electron moving through a potential difference of 1 volt. This is convenient for particle physicists because their experiments involve accelerating charged particles through electric fields, but it's a unit that makes no sense outside that specific context. Nuclear physics uses barns for measuring cross-sections, where 1 barn equals 10 to the minus 28 square meters. The name supposedly comes from physicists saying the target area was as big as a barn when they first measured nuclear cross-sections. It's a joke that became an official unit. Astronomy has magnitudes for brightness, a logarithmic scale where each step of 5 magnitudes corresponds to a factor of 100 in brightness. This bizarre system dates back to ancient Greek astronomer Hipparchus, who classified stars into 6 magnitude classes by eye. Modern photometry has made the system precise, but kept the counterintuitive structure where brighter objects have lower magnitude numbers. All of these units seem strange if you're not in the field, but they persist because they're useful for practitioners, because too much infrastructure assumes them, and because coordinating a change across an entire scientific community is nearly impossible. The parsec is just one example of a broader pattern. Scientific practice is full of arbitrary conventions that become entrenched. Sometimes this is fine. The choice doesn't matter much, as long as everyone uses the same standard. Sometimes it causes problems. Students struggle to understand parsecs because the definition seems backwards and arbitrary. Public science communication suffers because explaining parsecs requires explaining parallax, arcseconds, and ancient Babylonian mathematics. Most science communicators just convert to light years and move on. But professional astronomers are stuck with parsecs for the foreseeable future. Let me take you deeper into just how precise modern parallax measurements have become, and how this precision has only further cemented the Parsec's position. The Gaia spacecraft sits at a special point in space called Lagrange Point 2, about 1.5 million miles from Earth, in the direction away from the Sun. At this location, Earth's gravity and the Sun's gravity balance in such a way that Gaia orbits the Sun at the same rate as Earth, maintaining a constant position relative to our planet. This is crucial for parallax measurements. Gaia needs to stay away from Earth's atmosphere and thermal fluctuations while maintaining a stable observing platform. The spacecraft slowly rotates, completing one rotation every 6 hours. As it spins, its two telescopes scan across the sky, detecting and measuring the positions of stars. Over the course of its mission, Gaia has observed each star an average of 70 times, building up a precise picture of its position and how that position changes over time. The precision is staggering. Gaia can measure stellar positions to an accuracy of about 24 micro-arc-seconds for the brightest stars. A micro-arc-second is 1/1,000,000th of an arc-second. Remember, Bessel was working at the edge of human capability to measure about 300 milliarc-seconds, 3/10ths of an arc-second. Gaia is over 10,000 times more precise. To give you a sense of scale, 24 micro-arc-seconds is equivalent to measuring the width of a human hair from a distance of 1,000 miles. It's the angle subtended by a period at the end of a sentence, viewed from the distance between Earth and the Moon. It's the angle you'd need to measure to detect someone on the International Space Station winking at you. This precision allows Gaia to measure accurate parallaxes for stars up to about 10,000 parsecs away. Beyond that distance, the parallax becomes too small, even for Gaia to detect reliably. But 10,000 parsecs encompasses a huge volume of the Milky Way. It includes essentially every visible star, most of the galactic disk, and extends well beyond our local spiral arm. With this data, astronomers have created three-dimensional maps of stellar positions throughout our region of the galaxy. These maps reveal the true shape of spiral arms, identify stellar streams from dissolved clusters, trace the orbits of stars around the galactic center, and map the distribution of different stellar populations. Every single one of these maps uses parsecs as the distance unit. The software that generates these maps takes Gaia's parallax measurements in arc-seconds and converts them directly to distances in parsecs using the simple inversion formula. Distance in parsecs equals 1 divided by parallax in arc-seconds. The entire analysis pipeline assumes this relationship. Changing to a different unit would require rewriting millions of lines of code, updating countless analysis scripts, and converting terabytes of data. It's technically possible, but it would be an enormous undertaking with no clear benefit. And here's something fascinating about how Gaia's precision has revealed complications in the simple parsec definition. At the precision Gaia achieves, you can't just use simple Euclidean geometry anymore. Einstein's general relativity starts to matter. Light from distant stars gets bent very slightly by the sun's gravity as it passes through the solar system. This bending changes the apparent position of stars by amounts comparable to what Gaia measures. So the Gaia data processing pipeline includes relativistic corrections. It accounts for light deflection by the Sun, by Jupiter, by Saturn, even by Earth itself. It accounts for the fact that time runs at slightly different rates at different distances from the Sun due to gravitational time dilation. It accounts for aberration effects arising from the finite speed of light combined with Gaia's motion through space. The modern parsec, as officially defined by the International Astronomical Union, is no longer just the simple geometric construction Bessel would recognize. It's a precisely defined unit that incorporates all these relativistic effects. The IAU formally updated the Parsec definition in 2015 to account for relativity. The full definition now specifies that 1 parsec is the distance at which one astronomical unit subtends an angle of 1 arcsecond, measured in a coordinate system at rest with respect to the solar system barycenter, with appropriate corrections for light, travel time, and relativistic effects. It's a mouthful, but it's necessary to maintain the precision modern astronomy requires. This level of precision has opened up entirely new ways to use parallax measurements. Astronomers can now detect the wobble of stars caused by orbiting planets using parallax data. As a star moves through space, it follows a straight-line trajectory called its proper motion. But if the star has planets, the star actually wobbles slightly around the center of mass of the star-planet system. This wobble is tiny, but Gaia can detect it for nearby stars with large planets. By measuring the amplitude and period of the wobble, astronomers can determine the planet's mass and orbital period without even detecting the planet directly through other methods. Parallax data can also reveal binary stars that weren't known before. If 2 stars orbit each other closely, they appear as a single point of light, even through large telescopes. But their combined parallax measurement will show periodic variations as the 2 stars orbit, changing their average distance from Earth slightly throughout their orbital period. Gaia has discovered thousands of previously unknown binary systems this way. The data has revealed that binary stars are far more common than we thought. Perhaps half of all stars exist in binary or multiple star systems rather than as single stars like our Sun. This has profound implications for understanding stellar evolution, planet formation, and the overall structure of the galaxy. None of this would be possible without the incredible precision of modern parallax measurements. And all of it is reported in parsecs, because that's the natural unit for the measurement technique. But Gaia's reach has limits. At distances beyond about 10,000 parsecs, parallax becomes unreliable, even with Gaia's precision. For more distant objects, astronomers must use other distance measurement techniques. These form what's called the cosmic distance ladder, a series of overlapping methods that allow us to measure ever greater distances. The first rung of this ladder is parallax. Direct geometric measurement, no assumptions required except basic geometry. This anchors all other distance measurements. The second rung uses stars called Cepheid variables. These are massive stars that pulsate regularly, expanding and contracting with periods ranging from days to months. In 1908, Henrietta Swan Leavitt discovered that there's a tight relationship between a Cepheid's pulsation period and its intrinsic brightness. Longer period Cepheids are intrinsically brighter. This means, if you measure a Cepheid's period, you know how bright it actually is. Compare that to how bright it appears, and you can calculate its distance. But here's the crucial point. To use Cepheids for distance measurement, you first need to calibrate the period-luminosity relationship. You need to know the exact relationship between period and brightness. The only way to do this is to measure distances to nearby Cepheids using parallax, then measure their periods and apparent brightnesses. This anchors the relationship. Gaia has observed dozens of nearby Cepheids with measurable parallaxes, providing the most accurate calibration ever of the period-luminosity relationship. And those calibrating distances are measured in parsecs. The Cepheid calibration is expressed as absolute magnitude as a function of period, where absolute magnitude is the brightness a star would have at a distance of 10 parsecs. 10 parsecs is the standard reference distance for absolute magnitude. Why 10 parsecs? Because it's a round number in the parsec system. If we used light years, the reference distance would be 32.6 light years, which is awkward. If we used miles, It would be about 310 trillion miles, which is absurd. 10 parsecs works, because parsecs are the established unit. The entire cosmic distance ladder is built on this foundation. Cepheids reach out to about 30 million parsecs, or 30 megaparsecs. Beyond that, they're too faint to observe individually. The next rung uses type Ia supernovae, stellar explosions that reach a consistent peak brightness. These can be seen across billions of parsecs, but they must be calibrated using distances to nearby supernovae measured with cepheids, which are calibrated using parallax. Every rung depends on the ones below it. And the foundation, the anchor for the entire system, is parallax measured in arcseconds and converted directly to parsecs. If astronomers wanted to change the distance unit, they'd need to redo this entire calibration in the new unit. They'd need to recalculate every Cepheid absolute magnitude, refit every supernova standardization, update every cosmological distance calculation. The amount of work this represents is staggering. Thousands of published papers would need their numbers reinterpreted. Hundreds of databases would need updating. Textbooks would need revision. And for what benefit? The Parsec works fine. Everyone understands it. The math is straightforward. There's simply no compelling reason to go through all that trouble. Let me also address a common misconception about the Parsec. Some people, when they first learn the definition, think that parsecs must be imprecise or approximate because they're defined using Earth's orbit, which changes slightly over time. Earth's orbit isn't a perfect circle. It's slightly elliptical, with the distance to the Sun varying by about 5 million miles between perihelion and aphelion. The orbital plane precesses slowly over thousands of years. The semi-major axis of the orbit changes slightly due to gravitational interactions with other planets. Doesn't this mean the astronomical unit changes, and therefore the parsec changes? The answer is no, because the astronomical unit is now defined as a fixed number. In 2012, the International Astronomical Union redefined the astronomical unit to be exactly 149,597,870.7 miles. This number was chosen to match the historical value closely, but now it's fixed by definition rather than measured. Similarly, the parsec is now a fixed unit defined in terms of the astronomical unit and the arcsecond. 1 parsec equals exactly 206,264.806247096 astronomical units. This bizarre number comes from the tangent function and the definition of the arcsecond, but now it's fixed. The parsec is no longer tied to any actual measurement of Earth's orbit. It's a defined standard, just like the meter is defined in terms of the speed of light rather than a physical bar kept in Paris. This is how modern metrology works. Base units are defined in terms of fundamental constants when possible, and derived units are calculated from the base units using exact mathematical relationships. The parsec is now part of this system of defined standards. It's arbitrary in origin, but precise in definition. Another interesting aspect of the parsec is how it scales for different distance ranges. For nearby stars, we use parsecs, or the abbreviation PC. For more distant objects within the galaxy, we use kiloparsecs, abbreviated KPC, where 1 kiloparsec equals 1,000 parsecs. For extragalactic distances, we use megaparsecs, abbreviated MPC, where 1 megaparsec equals 1 million parsecs. For cosmological distances, discussing the scale of the observable universe, we use gigaparsecs, abbreviated GPC, where 1 gigaparsec equals 1 billion parsecs. This scaling is convenient because it keeps the numbers reasonable at all distant scales. Saying the galactic center is 8.2 kiloparsecs away is more manageable than saying it's 8,200 parsecs away. Saying Andromeda is 780 kiloparsecs or 0.78 megaparsecs away is clearer than saying 780,000 parsecs. Saying the observable universe extends to about 14 gigaparsecs is more comprehensible than 14 billion parsecs. The metric prefix system works well with parsecs, which is part of why the unit has proven so durable. Compare this to light years, which don't have standard metric prefixes. Astronomers sometimes say kilolight years or megalight years, but these terms aren't standardized and aren't commonly used in professional literature. You're more likely to see distances given as thousands of light years or millions of light years, written out in words rather than abbreviated. This is slightly less convenient than the clean prefix system that works with parsecs. It's a small advantage, but it matters when you're writing hundreds of papers and want notation to be clear and concise. The parsec has also proven useful for a completely different reason that has nothing to do with parallax. In cosmology, when studying the expansion of the universe, there's a fundamental relationship discovered by Edwin Hubble in 1929. Distant galaxies are moving away from us at speeds proportional to their distance. This is called Hubble's law, though it's now often called the Hubble-Lemaitre law, to acknowledge that George Lemaitre proposed it theoretically before Hubble confirmed it observationally. The proportionality constant is called the Hubble constant, usually denoted h0. It tells you how fast the universe is expanding. The Hubble constant is conventionally expressed in units of miles per second per megaparsec. This means for every megaparsec of distance, recession velocity increases by so many miles per second. The current best measurement gives h0 as about 70 miles per second per megaparsec, though this value is somewhat controversial, with different measurement methods giving slightly different results. But the key point is that the standard units for the Hubble constant are miles per second per megaparsec, not per light year, not per mile, per megaparsec. Why? Because megaparsecs are the standard distance unit in cosmology, and this particular unit combination makes the numbers come out convenient. If you used light years instead, the Hubble constant would be about 21.5 miles per second per million light years. The decimal makes it slightly less clean. If you used miles, the Hubble constant would be about 2.3 times 10 to the minus 18th per second, which is an absurdly small number that gives no intuition. The megaparsec is scaled just right for cosmological distances, making the Hubble constant a reasonable two-digit number that's easy to remember and work with. This is another example of how the parsec has become entrenched. The entire framework of observational cosmology uses megaparsecs for distance and expresses the expansion rate in terms of megaparsecs. Thousands of papers report their measurements this way. All the standard formulas are written with megaparsecs. Changing would require not just converting numbers, but rethinking how we express fundamental cosmological relationships. It would be a massive disruption for no clear gain. There's also something poetic about the parsec that I haven't mentioned yet. When you look up at a star that's 1 parsec away, you're seeing light that left that star about 3.26 years ago. The light has been traveling through space for that entire time, crossing the incomprehensible emptiness between stars. For a star 10 parsecs away, you're seeing it as it was 32.6 years ago. For a star 1,000 parsecs away, you're seeing it as it was 3,200 years ago, back when ancient Egypt was in its prime, and Homer was composing the Iliad. For the galactic center at 8.2 kiloparsecs, you're seeing light that left 26,000 years ago, before the peak of the last ice age, when Neanderthals still lived alongside modern humans. For Andromeda at 780 kiloparsecs, you're seeing light from 2.5 million years ago, when our ancestors were just beginning to make stone tools. Every time you look at the night sky, you're looking backward through time. The deeper you look into space, the further back you see. And the parsec provides the scale for measuring these distances, and therefore these look-back times. This time-distance connection is fundamental to astronomy. We can never observe the universe as it is now, only as it was when the light we're receiving left its source. The universe beyond our solar system is essentially a time machine, with more distant objects showing us earlier epochs of cosmic history. The parsec, arbitrary though its definition may be, gives us the ruler for measuring our journey through this time machine. When we say a galaxy is 1 billion parsecs away, we're saying it's 3.26 billion light-years away, which means we're seeing it as it was 3.26 billion years ago, less than a quarter of the age of the universe. The distance and the look-back time are inseparably linked, and the parsec provides the framework for thinking about both. There's one more aspect of the parsec I want to explore, which is how it relates to other cosmic distances and helps provide perspective on the scale of the universe. Consider our solar system. The distance from the Sun to Neptune, the outermost planet, is about 30 astronomical units or 4.5 billion miles. In parsecs, this is about 0.00015 parsecs, an absurdly small number. The solar system is tiny compared to even the nearest star. The Oort cloud, a spherical shell of icy objects surrounding the solar system and marking its gravitational boundary, extends to about 100,000 astronomical units, or roughly 1.6 light-years. That's about 0.5 parsecs. So the entire solar system, including its most distant gravitationally bound objects, fits within about half a parsec. The nearest star, Proxima Centauri, is 1.3 parsecs away. That means the distance to the nearest star is about 3 times the radius of the Oort cloud. Space is almost incomprehensibly empty. Moving outward, the nearest stellar nursery where stars are currently forming is the Taurus molecular cloud at about 140 parsecs. The center of the Milky Way is 8.2 kiloparsecs, or 8,200 parsecs away. The thickness of the galactic disk is about 1 kiloparsec. The diameter of the Milky Way's stellar disk is about 30 kiloparsecs. The distance to the Large Magellanic Cloud, a small galaxy orbiting the Milky Way, is about 50 kiloparsecs. The distance to Andromeda, our nearest large galactic neighbor, is 780 kiloparsecs, or 0.78 megaparsecs. The diameter of our local group of galaxies, including the Milky Way, Andromeda, and about 50 smaller galaxies, is about 3 megaparsecs. The Virgo cluster, the nearest large galaxy cluster, is about 16.5 megaparsecs away. The Virgo supercluster, which includes our local group, is about 33 megaparsecs across. The Laniakea supercluster, an even larger structure of which Virgo is a part, is about 160 megaparsecs across. The edge of the observable universe is about 14,000 megaparsecs or 14 gigaparsecs away. These numbers show the nested hierarchy of cosmic structure, from planets to stars to stellar nurseries to galaxy groups to galaxy clusters to superclusters to the cosmic web that spans the entire observable universe. And the parsec provides the measuring stick for essentially all of it, except the very smallest planetary scales. It's the unit that connects human measurement capability through parallax to the largest structures in the cosmos, through the cosmic distance ladder. This universality is another reason why changing would be so difficult. The parsec isn't just used for one type of object or one distance range. It's the standard from stellar distances to cosmological distances, from a few parsecs to gigaparsecs. Any replacement would need to work equally well across this entire range, which is 18 orders of magnitude in distance. That's a trillion times from the smallest to the largest scales. Finding a unit that works well across that entire range is challenging. The Parsec does it, partly through fortunate accident that it's scaled appropriately, partly through the metric prefix system that allows kiloparsecs, megaparsecs, and gigaparsecs. Light years could do it too with appropriate prefixes, but they're not established in the literature, and changing would require that massive coordination effort we've discussed. So we're left with parsecs, strange and arbitrary, but functional and entrenched. Let me give you one more perspective on why the parsec persists by examining what would actually need to happen if astronomy decided to switch units tomorrow. Imagine a hypothetical decree from some international astronomical authority declaring that effective next year, all distances must be reported in light years instead of parsecs. What would this require? First, every major astronomical database would need conversion. The Simbad database, maintained by the Centre de Données Astronomiques de Strasbourg, contains information on over 13 million astronomical objects. Every distance entry would need conversion. The NASA Exoplanet Archive lists thousands of confirmed exoplanets with their distances, conversion needed. The Gaia Archive with nearly 2 billion stellar positions and parallaxes, conversion needed. The 2-micron All-Sky Survey, the Sloan Digital Sky Survey, the Hubble Source Catalog, dozens of other major databases. All need conversion. This isn't just running a simple conversion factor through a spreadsheet. These databases have complex structures with relationships between different measurements. Distances affect calculated properties like absolute magnitude, space velocities, and galactic coordinates. Every derived quantity that depends on distance would need recalculation. The software that manages these databases would need updates. The APIs that researchers use to query them would need modification. The documentation would need rewriting. This represents thousands of hours of programming and testing work across multiple institutions and countries. Second, every analysis tool and software package would need updates. Professional astronomers use specialized software for working with astronomical data. Programs like IRAF, TopCat, Astropy, DS9, and hundreds of others. These tools assume parsec inputs in many places. Converting would require identifying every location in the code where distance units are assumed, adding conversion factors or unit specifications, testing to ensure nothing breaks, updating documentation and tutorials, and releasing new versions. For a large software project, this could be months of work. Multiply that across hundreds of packages, and you're talking about many person-years of effort. Third, the scientific literature would become fragmented. We have over a century of published astronomy papers reporting distances in parsecs. These papers don't become invalid just because we switch units, but they become harder to compare directly with new work. A researcher reading a paper from 1995 that reports a distance of 42 parsecs would need to mentally convert to 137 light-years to PaperLISF, compare with new measurements reported in light years. This is doable, but it's friction. It slows down research. It increases the chance of errors when people forget to convert or use the wrong conversion factor. The scientific literature is supposed to build on previous work. Having different units in old versus new papers makes that building process harder. Fourth, education would face a transition period. Textbooks would need updating, which happens slowly as new editions are published. For several years, students would encounter both units, old books using parsecs and new ones using light years. Professors trained in parsecs would need to retrain their intuitions. A professor might instinctively think 40 parsecs is a reasonable distance for a certain type of object, but would need to remember that's actually 130 light-years and recalibrate their expectations. This adjustment period would be confusing and error-prone. Fifth, And perhaps most significantly, individual astronomers would need to rebuild their intuitions. When you work in a field for years, you develop a feel for what numbers are reasonable. An experienced astronomer looks at a measured distance of 80 parsecs and immediately knows whether that makes sense for the type of object being studied. They know that 80 parsecs is far enough to be out of our immediate neighborhood, but close enough to be in our spiral arm. They know that a star at 80 parsecs, with a certain apparent brightness, must have a certain intrinsic luminosity. These intuitions are built on experience with thousands of measurements, all in parsecs. Switching to light years means rebuilding those intuitions. 260 light years doesn't immediately mean the same thing, even though it's the same distance. It takes time and mental effort to recalibrate. All of this adds up to a massive collective cost. Now weigh that against the benefits. What do we gain by switching from parsecs to light years? Light years are more intuitive to the general public because they're defined by a fundamental constant, the speed of light. That's nice for science communication, but professional astronomers aren't doing their work for public understanding. They're doing science, and for science, the parsec works fine. Light years might be slightly easier to teach to students, though even that's debatable since parallax is the fundamental measurement technique, and parsecs arise naturally from parallax. Is easier public communication worth thousands of hours of conversion work, millions of dollars in software updates, years of confused literature, and the hassle of retraining thousands of scientists? Most astronomers would say no. The cost-benefit analysis doesn't support change. This is why arbitrary standards persist, not because they're optimal, but because they're good enough, and the cost of change exceeds the benefit. The parsec has passed the threshold where changing becomes nearly impossible without some external force demanding it, and no such force exists. There's no new physical theory that requires different units. There's no technological development that makes parsecs impractical. There's no international crisis demanding standardization. There's just a slightly awkward but functional unit that works well enough that nobody wants to go through the pain of changing it. This phenomenon appears throughout history, in many domains. The QWERTY keyboard layout I mentioned earlier persists despite being suboptimal because millions of people have learned to type on QWERTY keyboards and billions of keyboards use that layout. Switching to a more efficient layout, like Dvorak, would require retraining everyone and replacing every keyboard. The benefit, slightly faster typing, doesn't justify the cost. Railroad gauges vary by country because different regions standardized on different widths early in rail development. Spain uses a wider gauge than France, which creates problems at the border where trains must change gauge or passengers must transfer. Everyone acknowledges this is inefficient, but converting one country's entire rail network to match the other would cost billions and take decades. So the incompatibility persists. The English system of measurement, with its feet, inches, miles, pounds, and ounces persists in the United States, despite the metric system being objectively superior for scientific work and easier to learn. Why? Because converting would require changing every road sign, every product label, every building code, every recipe, every tool, and retraining 300 million people to think in different units. The cost is enormous, and the benefit, while real, isn't compelling enough to motivate the change. The parsec is astronomy's QWERTY keyboard, its unique railroad gauge, its feet and inches. Arbitrary in origin, functional in practice, and locked in by accumulated infrastructure and practice. Now let me address one more common question about the parsec. If it's so arbitrary and based on ancient angle measurements, couldn't we at least redefine it to be a round number in terms of more fundamental units? For example, couldn't we define the parsec as exactly 10 to the 16th meters or some other power of 10? We could, but we won't, because that would break the simple relationship between parallax and distance that makes the parsec useful in the first place. Remember, the whole point of the parsec is that distance in parsecs equals 1 divided by parallax in arcseconds. This is a direct consequence of the geometric definition based on 1 astronomical unit and 1 arcsecond. If we redefined the parsec to be a round number of meters, this relationship would break. Instead of distance equals 1 over parallax, you'd have distance equals some conversion factor divided by parallax. The elegance would be lost. Every parallax measurement would require multiplication by a conversion factor before giving you distance. This defeats the original purpose of defining the parsec. The International Astronomical Union considered this when they updated various astronomical constants in 2012 and 2015. They explicitly decided to keep the parsec defined geometrically in terms of the astronomical unit and arcsecond, even though this produces an irregular number when expressed in meters. The geometric definition is more useful for astronomers than a metrically round value would be. This highlights an important principle in measurement standards. Units don't need to be neat in terms of other units. They need to be useful for their intended purpose. The parsec is awkward when expressed in meters. 30.857 trillion, 30.857 times 10 to the 15th meters. But it's elegant when used for parallax measurements, which is what it was designed for. That's what matters. Similarly, the electron volt is a strange unit from a metric perspective. 1 electron volt equals about 1.6 times 10 to the minus 19 joules, an irregular number. But for particle physicists, the electron volt is natural because it's the energy gained by an electron accelerated through 1 volt of potential. Their experiments involve accelerating particles through electric potentials. So, electron volts are the natural unit, even though they don't fit neatly into the SI system. The barn, that nuclear physics cross-section unit I mentioned earlier, equals exactly 10 to the minus 28 square meters. At least that's a power of 10, but it's still arbitrary. The name supposedly comes from physicists joking that hitting a nucleus was as easy as hitting the broad side of a barn. It's silly, but it works because it's scaled appropriately for nuclear cross-sections. Typical cross-sections are measured in millibarns or microbarns, which are convenient numbers. Expressing the same values in square meters gives ridiculous numbers, like 10 to the minus 31 square meters. Which would you rather work with? The parsec follows the same logic. It's irregular in terms of SI base units, but it's natural for the measurements astronomers actually make. That's sufficient justification for its existence and continued use. Let me take you through one more concrete example of how parsecs work in modern research to show you how deeply embedded they are. Imagine you're an astronomer studying a class of stars called RR Lyrae variables. These are old stars that pulsate regularly, with periods less than 1 day. They're important for understanding stellar evolution and for measuring distances because, like Cepheids, they have a relationship between their properties and their intrinsic brightness. You want to measure distances to RR Lyrae stars in a globular cluster, a dense spherical group of old stars orbiting in the halo of the Milky Way. You start by searching the Gaia catalog for known RR Lyrae stars in your target cluster. Gaia has identified thousands of RR Lyrae stars and measured their parallaxes. The catalog lists parallax in milliarc seconds and distance in parsecs. For your cluster, Gaia gives an average parallax of about 0.125 milliarc seconds. That's 0.000125 arcseconds, incredibly tiny. Using the standard formula, distance equals 1 divided by parallax in arcseconds. Distance equals 1 divided by 0.000125. Distance equals 8,000 parsecs. Your cluster is 8 kiloparsecs away, placing it in the galactic halo well above the galactic disk. Now you use photometry to measure the apparent brightnesses of the RR Lyrae stars in your cluster. You observe in multiple wavelength bands to determine their colors and correct for interstellar dust absorption. After corrections, you find the average apparent magnitude is about 15.5. You know from theoretical models that RR Lyrae stars have an absolute magnitude of about 0.6. That's their brightness at a distance of 10 parsecs. Using the distance modulus formula, apparent magnitude equals absolute magnitude plus 5 times the logarithm of distance in parsecs minus 5. You can verify your distance is consistent. 15.5 equals 0.6 plus 5 times log of 8,000 minus 5. 5 times log of 8,000 is about 19.5. 19.5 minus 5 is 14.5. 0.6 plus 14.5 is 15.1. Close enough to your measured 15.5 given uncertainties. The parallax distance and the photometric distance agree. Your cluster is definitely about 8 kiloparsecs away. Everything in this analysis uses parsecs. The Gaia parallax converts directly to parsecs. The absolute magnitude is defined at 10 parsecs. The distance modulus formula explicitly uses parsecs in its logarithm. Converting to any other unit would require changing all these formulas and relationships. The analysis would still work, but it would be more cumbersome because you'd need conversion factors scattered throughout. The parsec makes everything flow naturally. This is a typical analysis in modern astronomy. Thousands of papers use similar logic, working entirely in parsecs because that's the natural unit for the measurements and the theoretical framework. Changing would be possible, but would add friction to every calculation. There's one more dimension to the parsec that I haven't fully explored, which is its role in astronomy education and how students learn to think about cosmic distances. When a student first learns astronomy, they encounter a progression of distance scales. In the solar system, we use astronomical units. For nearby stars, we introduce light years because they're intuitive, light traveling for years. Then we introduce parsecs, which causes confusion. The student asks, why do we need yet another unit? Can't we just stick with light years? The professor explains that parsecs are what professional astronomers use, that they arise naturally from parallax measurements, that they're the standard in the field. The student, not unreasonably, thinks this seems like an arbitrary complication. And they're right. It is arbitrary, but it's also necessary if the student wants to read professional literature or work in astronomy. So the student learns parsecs, memorizes that 1 parsec equals 3.26 light years, practices converting back and forth, and gradually becomes comfortable with the unit. After a few years of using parsecs in coursework and research, the unit becomes second nature. The student develops those intuitions we've discussed. They know that 10 parsecs is nearby, 100 parsecs is still in our neighborhood, 1,000 parsecs is across the galaxy, and so on. The arbitrariness fades from consciousness. The parsec just becomes the distance unit, as natural as meters or kilograms. This educational process repeats for every new generation of astronomers, and each generation that learns parsecs becomes invested in continuing to use parsecs. They've spent years training their intuitions. They don't want to start over with a different unit, so they teach parsecs to their students, perpetuating the cycle. This is another mechanism that locks in arbitrary standards. Not just infrastructure and databases, but human capital, the trained intuitions and practiced skills that took years to develop. Changing units means devaluing that human capital, forcing experienced scientists to retrain. Nobody wants to do that voluntarily. Compare this to a field that successfully changed its units. Temperature in science used to be measured in Fahrenheit, at least in English-speaking countries. But the scientific community gradually shifted to Celsius and then to Kelvin for theoretical work. This shift was possible because temperature units are relatively simple to convert, because Celsius and Kelvin have a clear advantage in theoretical physics, where absolute zero matters, and because the change happened gradually over decades, as scientists adopted the better unit, one paper at a time. Astronomy could theoretically make a similar shift from parsecs to light years. It would take decades. It would require young astronomers choosing to use light years in their papers despite parsecs being standard. It would require textbooks gradually shifting emphasis. It would require database maintainers supporting both units during a transition period. It would require funding agencies agreeing not to penalize researchers for using non-standard units during the transition. It would require immense coordination and sustained effort across the entire global astronomical community. And at the end, what would we have? A distance unit that's more intuitive to non-experts, but otherwise functionally similar to what we had before. The benefit doesn't justify the cost and disruption, so the shift won't happen. The parsec is here to stay. There's also something to be said for stability in scientific practice. Having a consistent unit that doesn't change allows for easier comparison across time. A distance measured in parsecs in 1950 means the same thing as a distance measured in parsecs today, assuming corrections for refined measurements. If we kept changing units every few decades to chase theoretical elegance or public accessibility, the scientific literature would become harder to navigate. Historical papers would require constant translation. Consistency has value, even if it means accepting some arbitrariness. The parsec provides that consistency. It's been the standard for over a century. Papers from the 1930s through today all use parsecs. This allows direct comparison across nearly a century of research. That continuity is worth preserving. Let me give you one final example of the parsec in action, this time in cosmology, to show how it works at the largest scales. Astronomers studying the early universe look at extremely distant galaxies whose light has been traveling toward us for billions of years. The most distant confirmed galaxies are at redshifts around 13, meaning their light has been stretched by the expansion of the universe by a factor of 14. At this redshift, we're seeing the galaxy as it appeared when the universe was only about 300 million years old. The distance to such a galaxy is complicated to define because the universe is expanding. Do we mean the distance when the light was emitted? The distance now? The distance light actually traveled, accounting for expansion during its journey? These are all different numbers. Cosmologists use something called comoving distance, which accounts for expansion and represents where the galaxy is now in the expanding universe. For a redshift of 13, the comoving distance is about 9,000 megaparsecs, or 9 gigaparsecs. That's 9 billion parsecs, 29 billion light-years. All the mathematics of cosmological distance uses megaparsecs. The Hubble constant, as I mentioned, is measured in miles per second per megaparsec. The cosmological distance measure formulas, which integrate over the expansion history of the universe, output distances in megaparsecs when you plug in the Hubble constant and other cosmological parameters. The entire computational framework of observational cosmology is built on megaparsecs. Switching to light years or any other unit would require rewriting all these formulas, updating all the analysis software, converting all the published measurements, and retraining everyone's intuition about what distance means in an expanding universe. It's simply not going to happen. The megaparsec is as firmly established in cosmology as the parsec is in stellar astronomy. And so we've come full circle. The parsec, born from Friedrich Bessel's parallax measurements in 1838, defined by Babylonian angle measurements from 4,000 years ago, has become the universal distance scale for professional astronomy. From the nearest stars a few parsecs away to the edge of the observable universe, 14 gigaparsecs away, the parsec provides the framework for measuring cosmic distances. It's arbitrary in its definition, based on nothing fundamental about the universe itself. But it's useful in practice, elegant in its relationship to parallax measurements, and entrenched in infrastructure, practice, and human intuition. Changing would be technically possible but practically impossible due to coordination costs and lack of clear benefits. So the parsec persists, a monument to historical accident, practical necessity, and the difficulty of coordinating change in large, complex systems. It's astronomy's strangest distance measure, and it's not going anywhere. Before I wrap up, let me share some fascinating stories about how the parsec has appeared in popular culture and how it's been misunderstood, because these misunderstandings reveal something important about how scientific units work. The most famous reference to parsecs in popular culture is Han Solo's boast in Star Wars that the Millennium Falcon made the Kessel Run in less than 12 parsecs. When the movie first came out in 1977, science fiction fans immediately noticed a problem. A parsec is a unit of distance, not time. It's like saying your car did the drive to work in less than 12 miles. It doesn't make sense. The line became infamous as a scientific error in an otherwise beloved film. Fans debated whether it was a mistake by the screenwriters, or whether Han Solo was deliberately spouting nonsense to test whether Luke and Obi-Wan knew anything about space travel. Over the years, various explanations have been proposed to make the line make sense. Some suggest that the Kessel Run involves navigating around black holes or gravitational anomalies, and a shorter distance means you found a more dangerous but more efficient route. The idea is that 12 parsecs refers to the length of the path taken, not the time required. By this interpretation, Han is boasting that he found a shortcut that most pilots couldn't navigate. Later Star Wars material, including novels and the film Solo, A Star Wars Story, has adopted this explanation. The Kessel Run is now described as a smuggling route through dangerous space where the challenge is finding the shortest path, and 12 parsecs is impressively short. Whether this was the original intention or a retcon to fix a mistake, it's at least internally consistent. But it does highlight how unfamiliar parsecs are to the general public. Most people don't immediately recognize it as a distance unit. It sounds like it could be a time unit, perhaps something to do with seconds. This has led to parsecs occasionally being misused in other science fiction as well. Some works use parsecs as if they're a measure of speed or time, apparently not realizing their distances. For professional astronomers, these mistakes are mildly amusing but understandable. The parsec is an obscure unit outside their field. There's no reason the average person should know what it means. But these pop culture references do serve a purpose. They've made parsecs more familiar to the public, even if imperfectly understood. When astronomers talk about distances in parsecs, in science communication, at least people have heard the word before, even if they're not sure what it means. That's something. The parsec has also appeared in various scientific contexts outside astronomy. Occasionally, other fields borrow the unit for analogous purposes. Computer scientists sometimes jokingly refer to large data distances or transmission delays in parsecs, playing on the connection between distance and light travel time. Since information can't travel faster than light, the time required to send data across interstellar distances becomes relevant if you're thinking about hypothetical future communication networks spanning multiple star systems. A message to a receiver 1 parsec away would take at least 3.26 years to arrive. No matter how advanced your technology, you can't beat that limit. So parsecs become a natural unit for thinking about communication delays in speculative scenarios involving interstellar networks. These uses are usually tongue-in-cheek, rather than serious technical applications, but they show how the Parsec has entered broader scientific culture. Let me also talk about a fascinating property of parallax measurements that I haven't fully explored yet. Parallax provides absolute distances. By absolute, I mean the distance doesn't depend on assumptions about the object you're measuring. You don't need to know what type of star it is, how bright it intrinsically is, what its mass is, or anything else about its physical properties. You just measure an angle, use basic geometry, and you have a distance. This is incredibly powerful because it means parallax measurements can calibrate other distance methods that do require assumptions. For example, using Cepheid variables for distance measurements requires knowing their intrinsic brightness, which we determine by measuring parallax to nearby Cepheids. Using the brightness of a supernova to estimate distance requires knowing how bright supernovae are intrinsically, which we calibrate by measuring distances to galaxies with supernovae using methods ultimately tied back to parallax. The entire cosmic distance ladder rests on parallax as its foundation, because parallax is the only purely geometric method we have that requires no assumptions about the physics of the objects being measured. This makes parallax measurements uniquely trustworthy. If a parallax measurement gives you 800 parsecs and a different method gives you 1000 parsecs, you trust the parallax. There might be systematic errors in how the parallax was measured, certainly, but at least you know the method is fundamentally sound. It's just geometry. The other method might involve assumptions about stellar evolution or interstellar dust or population statistics that could be wrong. This foundational role of parallax in the distance ladder is another reason why parsecs are so entrenched. They're not just convenient for parallax measurements. They're essential for the entire structure of distance measurement in astronomy. Every other method ultimately gets calibrated in parsecs because parsecs are the units that parallax naturally produces. Changing to a different unit would mean recalibrating the entire distance ladder in that unit, which brings us back to the coordination problem we've discussed. There's one more philosophical dimension to the parsec I want to explore, which relates to the nature of measurement and how humans understand the world. Measurement is always an act of comparison. To measure something, you compare it to a standard. When you measure a table as 2 meters long, you're saying the table is twice as long as a 1 meter standard. When you measure a star as 50 parsecs away, you're saying the star is 50 times as far as the distance defined by 1 parsec. But where do the standards come from? Historically, many measurement standards were defined by human scale objects or arbitrary conventions. The foot was based on the length of a human foot. The inch was based on the width of a thumb. The mile came from millipassus, 1,000 paces by a Roman soldier. These standards were useful because they related to everyday human experience, but they were also arbitrary and varied by location. Different regions had different definitions of the foot or the mile. The scientific revolution brought a desire for universal standards that didn't depend on human body parts or local conventions. The meter was originally defined as 1/10,000,000th of the distance from the equator to the North Pole along a meridian through Paris. Later, it was defined by a physical bar kept in Paris. Still later, it was defined by a specific number of wavelengths of a particular color of light. Now it's defined in terms of the speed of light and the second, tying it to fundamental physical constants. This progression represents a search for increasingly universal and precise standards. The parsec sits in an interesting middle ground in this progression. It's not based on human body parts, so it's more universal than the foot or inch. But it's not based on fundamental physical constants either. It's based on astronomical geometry and human angle conventions. It's tied to Earth's orbit, and to the Babylonian division of circles into degrees. An alien civilization would not naturally arrive at the parsec. They might define a similar unit based on their own parallax measurements, but the numerical value would depend on their planet's orbital size and their angle system. From a philosophical standpoint, this raises interesting questions about the nature of scientific units. Should we strive to base all units on fundamental constants, removing arbitrary human conventions, or is it acceptable, even preferable, to have units that reflect how measurements are actually made, even if they incorporate some arbitrariness? The International System of Units, the SI system, takes the first approach. All SI base units are now defined in terms of fundamental constants like the speed of light, Planck's constant, and the charge of the electron. This makes the units universal in principle. Any civilization anywhere in the universe could recreate the SI definitions from physical constants. But astronomy has chosen not to fully adopt this approach. Yes, the astronomical unit is now defined as a fixed number of meters, tying it to the SI system. But the parsec remains defined geometrically based on the astronomical unit and the arc second, preserving its connection to actual measurement practice. This suggests that for working scientists, practical utility matters more than philosophical elegance. The parsec is useful because it aligns with how astronomers actually measure distances. Tying it to fundamental constants would make it more universal but less useful. So astronomy has made a pragmatic choice, accepting some arbitrariness in exchange for practical convenience. This is probably the right choice. Science is ultimately about understanding nature, and whatever units help us do that most effectively are the units we should use. If parsecs, with all their historical baggage and arbitrary definition, serve that purpose, then parsecs are justified. The universe doesn't care what units we use to describe it. The physics works the same whether we measure distances in parsecs, light years, meters, or units we haven't invented yet. The choice of units is a human concern about making calculations easier and communication clearer, and for the community of professional astronomers, parsecs do that job well enough that changing isn't worth the effort. Let me now bring all these threads together and give you a final perspective on what the parsec really represents. The parsec is more than just a unit of distance. It's a window into how science actually develops, as opposed to how we sometimes imagine it develops. We like to think of science as purely rational, building logically from first principles to increasingly sophisticated understanding. And in many ways, it is. But science is also a human activity carried out by people embedded in historical and social contexts. Those people make choices, some brilliant and some arbitrary. Those choices become embedded in practice, sometimes for very good reasons, and sometimes simply because that's how things were done, and changing is difficult. The parsec embodies this dual nature of science. On one hand, it's a clever and elegant solution to a real problem. How do you convert parallax measurements to distances efficiently? Define a unit where the conversion is trivial. That's genuinely smart. On the other hand, the specific value of that unit, based on 1 arcsecond of parallax, is completely arbitrary. It reflects ancient Babylonian angle conventions that have nothing to do with the physics of the cosmos. The parsec works despite this arbitrariness, not because of it. And it persists because of network effects, institutional momentum, and the high coordination costs of change. Not because it's optimal in any objective sense. This is how much of science actually works. Brilliant insights and clever solutions coexist with historical accidents and arbitrary conventions. The accumulation of past choices constrains present options. What's optimal in theory often loses to what's established in practice. Change happens, but slowly, and only when benefits clearly exceed costs. The parsec is a case study in all of this. Every time you see an astronomical distance reported in parsecs, you're seeing the accumulated weight of history. You're seeing Bessel's 1838 parallax measurement. You're seeing Babylonian mathematics from 4,000 years ago. You're seeing the practical needs of 19th century astronomers doing calculations by hand. You're seeing a century of scientific papers building on each other using a common unit. You're seeing the reluctance of institutions to undergo costly transitions without clear benefits. You're seeing how arbitrary choices, once made, can become effectively permanent through network effects. All of that is compressed into a simple 3-syllable word and a number: 50 parsecs, 800 parsecs, 14 gigaparsecs. Behind each number is this entire history, this entire set of choices and consequences. That's the parsec, a strange distance that makes no sense when you look at how it's defined, but perfect sense when you understand why it exists and why it persists. It's arbitrary and elegant, absurd and useful, a historical accident and a practical necessity. It's a reminder that science, for all its power and precision, is done by humans. And humans make choices that stick, for better or worse, long after the original reasons for those choices have faded from memory. The parsec will likely still be astronomy's standard distance unit a century from now, long after everyone reading this is gone, long after the telescopes and satellites we currently use are obsolete and forgotten, long after our current theories of cosmology have been refined or revised. The parsec will remain, a constant in an ever-changing field, a monument to the difficulty of changing established practices. And that's okay. Science doesn't need perfect units. It needs units that work well enough to let scientists do their work effectively. The parsec does that. It always has, since Bessel's time through to today's era of Gaia and exoplanet studies and cosmological surveys. It will continue to do that for the foreseeable future, strange, arbitrary, and utterly irreplaceable. The parsec is astronomy's most enduring quirk, and understanding why it persists tells us as much about how science works as any discovery about the cosmos itself. When you look up at the stars tonight, remember that those points of light are separated from us by distances measured in parsecs. Not because parsecs are the best possible unit, but because they're good enough and we're stuck with them. And sometimes, in science as in life, good enough combined with established is better than optimal but unfamiliar. That's the lesson of the parsec, a strange distance that makes no sense, except that it makes perfect sense once you understand the full context. Thanks for joining me on this journey through the history, mathematics, and sociology of astronomy's strangest unit. The next time someone mentions parsecs, you'll know exactly what they mean and exactly why we use them. And you'll appreciate the strange path by which an ancient Babylonian angle system became the foundation for measuring the cosmos. The switching costs are too high, the benefits too unclear, and the unit works well enough despite its oddity. So when you read an astronomy paper and see distances measured in parsecs or kiloparsecs or megaparsecs, remember what you're really seeing. You're seeing the accumulated weight of history. You're seeing Friedrich Wilhelm Bessel's 1838 measurement technique. You're seeing the Babylonian sexagesimal system for angle measurement. You're seeing the practical convenience of a unit that makes parallax arithmetic simple. You're seeing institutional momentum and network effects that make changing difficult. You're seeing how arbitrary choices, once embedded in practice, become effectively permanent. The parsec is strange, arbitrary, and based on ancient conventions that have nothing to do with the physics of the cosmos. But it's also useful, well-established, and unlikely to change anytime soon. Proxima Centauri sits 1.302 parsecs away. Sirius sits 2.64 parsecs away. Betelgeuse sits somewhere around 170 parsecs away. though uncertainty remains. The galactic center sits about 8.2 kiloparsecs away. Andromeda sits 780 kiloparsecs away. These numbers tell stories. Stories of light traveling for years across incomprehensible emptiness. Stories of stellar birth in collapsing gas clouds. Stellar evolution through nuclear fusion stages. Stellar death in supernovae or planetary nebulae. Stories of galaxies forming, colliding, evolving over billions of years. Stories of the universe expanding, carrying galaxies away from each other at speeds proportional to their distance. The parsec is just the unit we use to measure these stories. It's not the stories themselves. The cosmic distances exist whether we measure them in parsecs, light years, miles, or units we haven't invented yet. The stars don't care what units we use. Proxima Centauri would be just as far away if we measured in light years or in units based on Planck lengths or in some completely different system. Distance is distance. But we're human, and we need units to comprehend and communicate distances. Our brains didn't evolve to understand. We need numbers that fit on paper, that we can calculate with, that we can discuss and compare. And for astronomy, for historical and practical reasons that made sense in their time and that persist through institutional momentum, that unit is the parsec, strange, arbitrary, and utterly entrenched. The history of the parsec teaches us something important about how science actually works. Science isn't just pure logic and mathematical truth. It's also a human activity, carried out by people making practical decisions about how to do their work. Those decisions involve choices about tools, methods, units, conventions, and standards. Many of those choices are somewhat arbitrary. They're made for good reasons at the time, but different choices could have worked just as well. Once made, though, these choices become embedded. They shape how future work is done. They create path dependency, where later choices are constrained by earlier ones. Infrastructure grows around them, both physical infrastructure like instruments and databases, and social infrastructure like shared knowledge, training, and practice. Changing becomes difficult, not because the original choice was optimal, but because changing requires coordinating across many people and updating many systems. The cost of change grows, while the benefit often remains unclear. So arbitrary choices persist, sometimes for centuries, long after the original reasons for making them have disappeared. The parsec is a perfect example. It was chosen because it made parallax arithmetic convenient in the 1800s, when astronomers calculated distances by hand. That reason no longer applies. Computers handle the arithmetic now, but the parsec remains because too much of astronomy is built around it. This isn't a failure of science. It's just how complex human systems work. Optimal, in some abstract sense, doesn't matter as much as good enough. Combined with already established, the parsec is good enough. It won't change unless something forces the change. Some technological shift or theoretical development that makes the parsec actively harmful rather than merely arbitrary. No such development is on the horizon. So the parsec will likely still be astronomy's standard distance unit 100 years from now, long after everyone who first adopted it is dead. Long after the original parallax measurement technique has been obsolete for over a century. Future astronomers will learn parsecs in their textbooks, measure distances in parsecs in their research, and explain to curious students that yes, the definition is strange. No, there's no particular reason for it, beyond historical accident, and no, we can't change it because too much depends on it. And those future astronomers will be right. That's the parsec, a unit that makes no sense, defined by arbitrary ancient mathematics, persisting through sheer institutional momentum, useful enough that changing isn't worth the trouble. It's astronomy's strangest measurement, an echo of 1838 frozen in practice, a reminder that science is done by humans, and humans make choices that stick. Next time you see a distance measured in parsecs, you'll know exactly what you're looking at. Not just a number, but a historical artifact. A monument to Friedrich Bessel's precision, to Babylonian mathematics, to the practical needs of pre-computer astronomy, and to the difficulty of changing established practices. It's all of that, compressed into 3 syllables: parsec. The strange distance that makes no sense, but that we're stuck with forever. Thanks for sticking with this exploration of one of astronomy's most peculiar quirks. The parsec might be arbitrary, but the universe it helps us measure is anything but.